All right, let's do this problem. This one's going to be fun, I can tell you. All right, so let's look at this guy. Again, we're trying to write shear force and bending moment as a function. How many sets of equations do I need for this problem? 1, 2, 3, 4. Can you write a expression that's for the loading that's continuous across the structure? Yes. So you only need one set of equations. So at some distance x, I will cut it right here. And now you have to decide whether you want to work the left side or the right side. The left side, what kind of area is that? That is a trapezoid. What is the right side? That is a trapezoid. Well, no help there. I got a pin there. That's one unknown. I got a pin there. That's one unknown. So far, no difference. Except this side is all going to be in terms of x. And what would the other side be in terms of? 18 minus x. So I believe that you want to stay away from that. That just makes it a little more complex. So based upon that, I'm going to take the left-hand side. That one little difference. That all these terms will have a dimension of x, whereas all these area terms will have a dimension of 18 minus x. I think it would be easier to work the left side. And once I've made that choice, all I need is my A reaction. So there's my positive shear force at A. What's the moment at A? What's the bending moment at A? 0. So I want to find the A reaction. So I'll probably some moments at B and find the reaction at A. So now looking at this diagram, how am I going to get this? How am I going to break this up into something I can use? Yeah, that's usually the best way to do it, is to look at it as a triangle and a rectangle. So let's first do the rectangular force. I'll call that F1. Oops, not 0, F1. And we're going to do it from B, so that'll be a distance B1, D1. And then I'll have an equivalent force for the triangle. I'll call that F2, and it'll have a distance from B, F2. So let's find those to get started. So what would F1 be? So it's the area under this rectangular part of the curve. So it's base 18 times height 1. So F1 is going to be 18 kips. Everybody see that? What's D1 going to be? The distance from D to the centroid. What's going to be half of 18? So that'll be 9 feet. Now this is the one some people have a little trouble with. What's F2? Well, I only want this height for my triangle. And that's not 3, is it? 3 is the total height. I know this part here is 1. The total is 3, so this height is 2. So F2 is going to be 1/2 the base, which is 18 feet, times the height, which is 2 kips per foot. And that's also going to be, oddly enough, 18 kips. And then the distance from B to the centroid, D2, is what? Well, that's the tall end, so it'll be 1/3 the distance, and 1/3 of 18 is 6 feet. Everybody see that? Any questions about that?
D1, where's D1?
D1 goes from B, see that's D1 right there. It's this distance right here. And then D2 would be this distance. And these are both the centroids, right? This is the centroid of the rectangle. This is the centroid of the triangle.
So you don't want us to show moment is 0 at a pin? There's no moment?
You don't have to show it. It just comes that way, right?
Yes, so on the test we don't have to show it?
We don't draw it.
There's nothing to draw. There's no moment. Why would you draw it?
Okay. So we're not put that.
You know the moment is
0.
0. You don't have to write moment equals 0. You could if you like. But I think it's going to confuse you to come over here and you draw a moment arrow and then label it 0.
Okay. Just want to make sure you're not going to count off of that.
Oh no, why would I do that?
Thank you. Okay, I wasn't going to say that. Thank you.
All right, so I'm trying to find my reaction at A, so I'm going to sum moments at B. Is there a moment at B, Mr. Morris? Do I need to include it in my equation? Do I need to include a moment at B in my equation?
No.
Okay. Just want to check with you. So about B, F1 and F2 are going to create what kind of moment? Positive or negative? Both positive. So I'll just take them 1 and 2. So F1 is going to be 18 kips times a moment arm of 9 feet. And then F2 is going to also be 18 kips times a moment arm of 6 feet. And then way out here on the left is my shear force at A, which is going to create negative moment and have a moment arm of 18. So it looks like the shear at A is 15. You guys get 15? That's all I need. Because the moment is, everybody say it, 0. Not everybody said, only Mr. Head participated. Thank you. Oh, did you? Sorry, I didn't mean to discount everybody. I'll give everybody a chance to participate. Everybody say 0.
0.
Okay. Think of the 0 from you guys over there.
0.
Thank you. All right, so what do we do next? Are we done? We can be if you like. But I don't think we are. I now need you to draw a free body diagram of this left-hand side. I'll make it kind of big so we'll have plenty of room to see it. So that'll be at some length X. We just found the shear force. What was it? 15. And now I've got to deal with this trapezoid loading. Now I know here on the left side it's 1 kip per foot. But what is it here? So if I'm going to write an equation for the load as a function of x, I know at x equals 0 it's going to be 1 plus what? What's the slope of this line? What's the slope of this line? Rise over run. What's the rise? 3 minus 1 is 2 over 18. 2 over 18 is 1. X over 9 is 1/9. So that means on this side it's going to be 1 plus x over 9. And does that work? When x is equal to 0, I get what? 1. Well, that's what it is. When x is equal to 18, I get 2 plus 1 is 3. 3. It matches. So this will tell me the value of the intensity of this load as a function of x. And we're going to break that up into what? A triangle and a rectangle. And we're going to call this one, since I've already used F1 and F2, I'll call this F3 and F4 at a distance D3 and D4. So what is F3? It's base times height, so it's just going to be x. The distance from the cut to the centroid of this is half the distance. The distance is x. Half the distance is x over 2. What about x? What about the force 4 that represents the triangular part? Maybe I'll do this just so you can see it. I'll kind of cross-hatch it a little bit. What's that area? Well, it's triangle, so it's going to be 1/2 base. Base is x times the height. What is that height right there? Well, I know this height is 1 plus x over 9, and this height is 1, so this is going to be the difference, which is just x over 9. So that means F4 is going to be 1/2 base x times height x over 9, which looks like x squared over 18. Yeah?
Can you explain again how you got the slope of the...
Well, the slope is just the change in height over the change in distance, right? Rise over run. So it starts here at 3, but it starts at 1 and ends at 3. So what's the vertical change? 2. And then what's the distance it traveled?
18.
So 2 over 18, 1/9. Right? It's always x times the slope for a straight line. Now I got all that done. At the cut, I've got my positive shear, my positive bending moment. So all I do now is just what? Oh, I forgot one thing. I forgot to compute D4. What's the distance from this edge to the centroid?
X over 3.
Yeah, it's 1/3 the distance. The distance is x, so it'll be x over 3. So now with all this stuff, I should make sure this is in equilibrium. So I'll come back and some moments at the cut and make sure it's in equilibrium. And I'm going to use right-hand rule. With that sign convention, this moment is positive. F4 and F3 will also be positive. So I'll start with F3, so that'll be a force of x times a distance of x over 2. So this is going to be force 3 d3 plus F4, which is x squared over 18 times this distance, which is x over 3. So that's F4 d4. And what's left? The reaction way over here. And that's going to create what kind of moment? Positive or negative about the cut? Negative. And that's going to be 15 kips times the distance of x. So now we solve for the moment. So moment as a function of x will be the following set. So this is going to be the bigger term. So that's going to be x cubed over 54. And that will be negative x cubed over 54. This is going to be x squared over 2. And that's also negative. And this is going to be 15x. And that should have the units of kip feet. Mr. Morris, can we check that?
Yes.
How can we check it?
0.
0. What does that mean, 0?
The moment is 0 at 0.
So you're saying that the moment at a pin should be 0.
Yes.
And this pin is located at x equal
0.
So you put in x equals 0, what do you get?
0.
Yeah. What else? Can we check it somewhere else?
Oh, yeah.
Yes.
So we just checked that moment at x equals 0 should be 0, and our equation says yes. What else?
You check at 9.
At 9? Why 9?
Because we have that. Well, no. That's
Do we know the moment somewhere else? You're moving in the right direction. You're getting warmer. The other end, yeah. So the moment at x equal 18, which is this, should also have a moment of 0. And I can't do that one in my head. Why don't you guys check that one? Plug in 18 here. 18 cubed, 54. 18 squared over 2.
Bless
Bless you. Anybody getting that? I kind of feel good that it's going to be true, so I'm going to have my green check mark poised and ready. Is anybody checking?
Let's go. We here.
You got it? Oh, Mr. Head says good, so I'll go with that. So now I have to just get my shear. So I will sum forces in the y direction. Make sure I'm in equilibrium. I'll assume up is positive, so that shear force is down. F3, F4 are down. Let's see, F3 was x. F4 was x squared over 18. And 15 is up plus 15. So if I solve for the shear, it looks like I'm getting minus x squared over 18 minus x plus 15. And that will have units of kips. Do I know the shear anywhere? What is the shear force at x equals 0? We solved for it. VA. And VA was 15. Does this give you the value of 15 at when x is equal to 0? 0, 0, it does. My 2's a little funky there. Now we do know the shear at B, we just didn't solve for it. I could have summed forces in the y direction here and found the shear at B, and if I plug in x equal 18, that would be the shear at B. I didn't do that, but if you had time, you could check it. So I'm just going to write the shear at 18 would be whatever we computed the shear at B. We just don't know what that is, but you could do that.
21.
Okay. Yeah. Now, one thing we can check really quick is the derivative of the moment with respect to x equal to the shear? And the answer is yes. Hey, 17 minutes. You guys are getting better at this. Any questions? Okay.